Hey Math 30, welcome back. And in this video, we're going to be returning to limits. So we're going to be returning back to those concepts that we looked at in chapter 2. But we're going to be able to calculate some limits with a new tool called L'Hopital's rule, and it uses the derivative. So you might remember that back when we were in chapter 2, we didn't know the derivative yet. We didn't have the definition of the derivative. So we had to calculate limits using algebra and other means, or the graphs. And then now we know the derivative, and it turns out that the derivative can help you find certain limits with something called L'Hopital's rule. Now, it's a French name. It's pronounced L'Hopital. And we need to be able to recognize certain limits that are indeterminate forms 0 over 0 or infinity over infinity. I'll explain in a moment. If you get those forms, you can use L'Hopital's rule to calculate them. Let's just do a few. So, and let me switch over here, and I'll explain some examples of where that comes from, and then I'll show you some examples. Okay, so first, let's look at this function. This is f of x equals ln x over x minus 1. Let's first note that f of 1 is undefined. If you plug in 1, you don't get a number out. So f of 1 is ln of 1 over 1 minus 1. Well, what's that? Well, that would be 0 over 0. And you can't divide by 0, and what does 0 over 0 even mean? So this is undefined. So the function is undefined at 0 over 0. But we know that functions could, right? Functions could have just a whole at that point. You know, what if at 1, so the question is it a whole at the function? Is it an asymptote? We don't know. Plugging it in doesn't tell you enough. And we'll look at the graph in a minute, but we have no way of knowing, like, does the limit exist? So the question might be, okay, so the function doesn't exist at 1, but is it a hole in the graph? And if it's a hole in the graph, that means the limit does exist, but we don't know. So what is the limit? Well, we can actually look at the graph, and I'll show you the graph now. I've got it, actually here. Sorry, I clicked on the wrong tab. Here you go. So it turns out this is the graph of that function. I've got, let me make this a little bigger. Let me zoom in slightly. Okay, that should be okay. It's super not obvious that ln x over x minus 1 would create a hole at 1, but it does. And there's no way we could calculate the limit, this limit at x equals 1 using the techniques we did in chapter 2, because we can't factor ln. That doesn't make any sense. So yeah, so it turns out the limit as x approaches 1 is 1, because do you notice that from the right hand side, this is as we get closer and closer to the hole in the graph, from the right hand side, this is getting closer and closer and closer to y equals 1. See, when we're just to the right of it, y equals 0.99. And as we approach from the left, it's approaching y equals 1 as well. So we know the limit graphically, but what if we don't know the graph? How do we do that? Well, we need something called L'Hopital's rule, which I want to explain the rule, and then we'll actually come back and use L'Hopital's rule on this example. So just to summarize, we try to take the limit of this function that's undefined at its value. But we would find that the limit of ln of, the limit as x approaches 1 of ln of x equals 0. And we would get that, let me actually slide this down. And we would get that the limit as x goes to 1 of the denominator, which is x minus 1, also equals 0. So if we tried to apply the limit to the function, we would first say, hey, you know what? Let's look at the limit of the numerator, and the limit of the numerator approaches 0, and the limit of the denominator approaches 0. So the limit's getting closer to 0 over 0. And you might remember back in chapter 2, we called that an indeterminate form. If you ever get an indeterminate form, you basically don't know if the limit exists or not. Well, it turns out this limit exists. We just looked at the graph and we know what it is, but we don't have a way to calculate it yet. Okay, so The first thing for L'Hopital's rule that you need to do is you need to be able to determine an indeterminate form, or you need to recognize that your limit is an indeterminate form. So here are the two types we're going to look at. Suppose you are trying to calculate a limit, and ultimately you're trying to calculate this limit down here. You're trying to calculate the limit of a function divided by a function. Suppose the limit of the numerator equals 0 and the limit of the denominator equals 0 at the value you're interested in. So in this case, we're trying to find the limit as x approaches a. And the limit as x approaches a of the numerator, f, is 0, and the limit of the denominator is also 0. Then the limit is an indeterminate form of type 0 over 0. This is an example. I actually just wrote it on the other page. I guess I could have written it here. Note that the limit as x approaches 1 of ln is 0. So the limit of the numerator is 0. And the limit as x approaches 1 of x minus 1 is also 0. So we have an indeterminate form. Indeterminate form of type 0 over 0. Okay. One thing I want to point out right now, and I'm going to maybe repeat it a few times, is that does not mean that this equals 0 over 0. Do not write that. Don't write the limit of ln x over x minus 1 equals 0 over 0. This equals is meaningless in this case because 0 over 0 is not a number. So a limit can't equal 0 over 0. What you do is you write down the limit of the numerator and write down the limit of the denominator and show that they both equal 0, and then write a sentence saying this is indeterminate form of type 0 over 0. To do L'Hopital's rule, you first need to check this condition, and you need to show your work to check that condition. Okay, there's another indeterminate form. By the way, we're not going to calculate it yet. I'm going to do that on the next page. We'll come back and calculate it. But I just want to say that there is another way that this could be indeterminate. And that is if the limit of the numerator is infinity and the limit of the denominator is infinity, then the limit of the numerator over the denominator is indeterminate of type infinity over infinity. L'Hopital's rule also works if the numerator goes to infinity and the denominator goes to infinity. So the limit of the numerator is getting, so as x goes to infinity in this case, the limit of the numerator is getting closer to infinity, it's getting big, and the limit of x squared as x goes to infinity is also infinity. So we get an indeterminate form of type infinity over infinity. Okay, we'll come back and calculate that one in a minute. Let's just do this one. Oh, that's right. I threw in this example and I forgot. So this is an example of a limit. What if we wanted to find the limit of this function as x approaches 2? If you try direct substitution, you'll find that you get 0 over 0. Turns out we can calculate this limit using the old techniques. We can use the old techniques that we learned in chapter 2. So I'm going to use this example to show you the old way we used to do it, and then also show you L'Hopital's rule using the same example. So we're going to calculate the same limit two different ways. So review, remember, back in chapter 2, if we wanted to find the limit as x goes to 2 of x squared minus x minus 2 over x plus 3x minus 10, the first thing you would try is direct substitution, and you would say, okay, what does this equal? And you can try direct substitution, but what you will find is you're going to get 0 over 0. And let's just actually show that. So if you tried direct substitution, you would get 2 squared minus 2 over 2. Oh, sorry, that dropped a square. 2 squared plus 3 times 2 minus 10. And you would get 0. This is 4 minus 2 is 0. And this is 4 plus 6 minus 10 is also 0. Okay, so this is indeterminate. And you might be saying, hey, David, didn't you just violate the thing that you said not to do earlier? I did. Do you notice I wrote equals? Oops. Do you notice I wrote equals? So in other words, I'm saying this limit equals 0. That is something we want to avoid now, and that is meaningless. So actually, that's not true at all because this can't equal this. So I'm just going to erase it and say, I'm going to say this. So, oops. This means that the limit is indeterminate. We don't know. We don't know if it exists or not. Now you may remember that what we can do is we can factor and cancel and remove the discontinuity or remove the singularity. Okay, so let's copy that. Let's bring it down and all right. You may remember that what we can do is, in this case, because we have a polynomial on top and bottom, we can factor the numerator and denominator and cancel the common factors. Let's remember that technique. So this is a good place to start reviewing for old things, for the final exam. And you'll find that this factors as x minus 2 and x plus 1 over x minus 2, x plus 5. Okay, so do you notice that the problem with plugging in 2 is that it causes the numerator and denominator to both be 0, but when you factor, you can cancel, and we get the limit as x minus 2, the limit as x approaches 2, of x plus 1 over x plus 5. And now that we've gotten rid of the problem, we can actually do direct substitution, and I can write equals and it's valid because this ends up being 2 plus 1 over 2 plus 5 equals 3 over 7. And if we go to the graph, we can see that the function has a hole at 2. Right there. It is undefined at 2. Just like we found, you can't plug in 2. You get 0 over 0, which is undefined. But if we actually plot that point, 2 comma, and we just found that the limit is 3/7. Let me change the colors so they match. I'll just make them both black. And then I'll graph it as a hole. Then there is a hole in the graph right at the limit point we found. The limit's 3/7. The limit was at 2, x equals 2. So if we plot the point, 2 comma 3/7, it is the coordinates of the hole in the graph. And the function is undefined there. Okay, everything we just did was a review of chapter 2. This was not L'Hopital's rule. This was a review of the way we would have done this limit back in chapter 2 or on exam number 1. Here is how L'Hopital's rule works. I'm just going to kind of walk through an example, then we'll do the formal definition. Let's actually go back and we're going to calculate this limit again. Okay. So this is the old way, the old method. Now let's do L'Hopital's rule. Okay, L'Hopital's rule goes like this. So we've already checked that this is an indeterminate form. And what you would do is you would write, but I'm going to write it out again. So the limit as x approaches 2 of the numerator equals 0, and the limit as x approaches 2 of x squared plus 3x minus 10 also equals 0. The limit as x approaches 2 of, oh, I can copy this. I can paste this, I mean. I don't have to write this all again. Here we go. So this is indeterminate of type 0 over 0. That's the language we use to make the statement that this limit is indeterminate. On all these L'Hopital's rule problems, you need to first show that the limit is indeterminate. If you do, then you can do the following. It's a cool trick. Then instead of calculating this limit, we can calculate the limit of the derivative of the top, and we take the derivative of the bottom. So, and let me write that out. What we do is we do the limit of, and I'll switch to green. We actually take the derivative of the numerator, and we take the derivative of the denominator. Okay, let me pause for a sec. This is not quotient rule. This is not quotient rule. Instead of doing the limit of the original rational function, we're going to do the limit of the derivative of the numerator and the derivative of the denominator. And we replace this problem with that problem. Well, we have the limit as x goes to 2. What is the derivative of the numerator? It's 2x minus 1. What is the limit of the denominator? It's 2x plus 3. Do you notice that we can just do direct substitution right now? So let's just do it. So this is 2 times 2 minus 1 over 2 times 2 plus 3, which is 3 over 7. Do you see we got the same? We got 3 7s by factoring, canceling, and we got 3 7s by factoring, canceling, and doing direct substitution. And down here, we did a totally different method, which is we took the derivative of the numerator and got that. We took the derivative of the denominator and got that. We did direct substitution, and we got 3 7s. That's L'Hopital's rule. And here is the formal statement of it. And let's go through this so that you know it. Suppose you have two functions, f and g, and they're both differentiable. And furthermore, the derivative of f is 0. Or excuse me, sorry, I said that wrong. The limit as x goes to a of f is 0, and the limit of g as x goes to a is also 0. Or it could be that they're equal to infinity or negative infinity. Then, what that does is it creates a situation where either you have an indeterminate form of 0 over 0 or infinity over infinity. In that case, instead of calculating the original limit you wanted to calculate, you can instead calculate the limit of the derivatives of those functions. And it turns out it will give you the correct answer. It'll give you the same answer. Okay, so let's go back to the one that we looked at earlier, and then we'll just do it. So first, you must verify the limit is indeterminate. And I think we actually wrote that already. So I can just come back and copy this. And I will come back over here and paste it. Okay. Oops, I meant to sort of misclick that. Okay, there we go. I don't need these check marks. Okay, so the first thing you need to do is you need to verify the limit of the numerator is 0. The limit of the denominator is 0. So we have an indeterminate form of type 0 over 0. The other one we're going to be doing in this video is possibly looking at ones where the indeterminate form is infinity over infinity. So we're going to have both cases. Okay, so now that we've done that, we can replace our limit with the L'Hopital's rule. And that would be like this. So we got a pen. So the limit as x goes to 1 of ln of x over x minus 1 is equal to, now, since we have shown that we get an indeterminate form with the original limit, we can instead take the limit of the derivatives of the top and bottom. Well, what's the derivative of ln x? The derivative of ln x is 1 over x. What's the derivative of x minus 1? The derivative of x minus 1 is 1. What does this reduce to? Well, anything divided by 1 is itself. So this is 1 over x. But now I can do direct substitution, and I'm done. 1 over 1 equals 1. So the original limit that we were trying to find of ln of x over x minus 1 equals 1. Let's go back to the graph. Remember we looked at the graph of this earlier. And it's super not obvious, but the coordinates of the hole are 1, 1. I plotted it to make the graph look nicer. And as this function gets closer, as x gets closer to 1, y gets closer to 1. And as x gets closer to 1 from the left, y gets closer to 1 as well. Okay? Let's look at a couple more examples, and then you should know enough to do your homework. I might come back with another video with some more examples. This is one we looked at earlier. So the first thing you would do is you would say, well, what is the limit as x goes to infinity of the numerator? Well, as x goes to infinity, e to the x goes to infinity. And what about the limit as x goes to infinity of x squared? Well, that is also infinity. And so we have indeterminate, I'm just going to abbreviate, indeterminate of type infinity over infinity. So we can apply L'Hopital's rule. The limit as x goes to infinity of e to the x over x squared can be replaced with, so since it's indeterminate, it can be replaced with the limit of the derivatives. Well, what's the derivative of e to the x? It's e to the x. What's the derivative of x squared? It's 2x. Can you see that it's still indeterminate? So the limit as x goes to infinity of e to the x is still infinity, and the limit as x goes to infinity of 2x is still infinity. So our limit's still indeterminate. So what do? You apply L'Hopital's rule again. So sometimes you apply L'Hopital's rule and the result is still indeterminate. So you can apply L'Hopital's rule to that and then iterate and see where it takes you. So that means the limit as x goes to infinity of e to the x over 2x is the limit as x goes to infinity of, well, you just do L'Hopital's rule again. We're just coming down here and we're trying again. And we get the derivative of e to the x is e to the x. The derivative of 2x is 2. Now this is looking better. Now this is not indeterminate. We can do direct substitution. And the derivative of e to the x is infinity. And the derivative, sorry, I said the wrong thing. The limit as x goes to infinity of e to the x is infinity, and the limit as x goes to infinity of 2 is 2, and so this means that our limit is infinity. So it was not obvious that our original function, that the result of this original function is infinity. And the way we can show it is by doing L'Hopital's rule. Now you may remember back in by the way, just something to say. this is not an indeterminate form. Infinity over 2 is infinity. Remember that back in chapter 2, we said if you get infinity over a constant, then that means the numerator is growing as big as you want. And so the whole fraction is going to infinity. So the answer to this problem is infinity. And you can show that using L'Hopital's rule. Okay, one more example. And then I will do this one more example. So I'm just going to shorten it slightly to shorten the video. So you should show first that it is indeterminate of type infinity over infinity, because the natural log goes to infinity as x goes to infinity, and square root goes to infinity as x goes to infinity. So we can apply L'Hopital's rule. The limit of the ln over the square root of x is equal to the limit of the derivatives. So we just rewrite the limit, and the numerator is 1 over x, and the denominator is the derivative of, so remember, x square root of x is x to the 1/2. So we get this. And now if you just plugged in infinity in top and bottom, well, you would get infinity over infinity again. But actually, can you see that we can just do some algebra to reduce this? So this would be the limit as x goes to infinity. So in some cases, you can apply L'Hopital's rule again. Like this one, we could, because this is still indeterminate of type infinity over infinity. But you can also just go back to the methods we used in chapter 2, which is just use some algebra to reduce it and cancel anything if necessary, and then see if you can calculate the limit that way. Well, this would be there's a couple ways you can do this, but I know one way that students like to see is the numerator is 1 over x, the denominator is 1 over 2x to the 1/2. Because this negative exponent would, sorry, that was sloppy. This negative exponent would bring this x to the negative 1/2 down to the denominator. So I just wrote that down here. So then I can flip and multiply the fractions. And I get 2x to the 1/2 over x. And so that would be limit as x goes to infinity of 2 over x to the 1/2. And now so what I have is x to the 1/2 in the denominator. And so that means I have square root of x in the denominator. And what this approaches is 2 over infinity. So the denominator goes to infinity. And remember that if you have, this is the opposite of the previous example. This is like a review of chapter 2. If you have a limit where the numerator is going to a constant and the denominator is getting really big, it's going to infinity, then the top stays small and the bottom gets big. So the whole fraction goes to 0. So the answer to this one is 0. Oops, sorry, I didn't mean to zoom away that far. So let's just review. I took the derivative of the numerator, which is 1 over x, the derivative of the denominator, which is 1/2 x to the negative 1/2. Did a little exponent properties here and brought this x to the minus 1/2 down to the denominator in this fraction down here. I just flipped and multiplied, and we get this. X to the 1/2, and this is x to the 1 power. You can subtract the exponents and bring it down. I just did 2 steps in one, but it'll reduce to this. And then the denominator goes to infinity, and the numerator stays constant, so this whole fraction goes to 0. One last comment I want to make. I will do, so it turns out, so remember I've said you first need to check that the numerator and denominator are indeterminate. And here's an example of where things go wrong if you don't. So if you tried to apply L'Hopital's rule to this example, you will get garbage answers. You'll get a garbage answer that doesn't make any sense. So let's say we apply. So it turns out this is not indeterminate. Not indeterminate. Why? Because the sine of pi, notice the limit is going to pi from the left. The sine of pi is 0, but 1 minus cosine of pi is not 0. Cosine of pi is -1, so this is 1 minus -1, which equals 2. So what we get is 0 over 2, which is not an indeterminate form. So this is a case where if you just look at it and go, oh, this must be L'Hopital's rule, I'll just apply it. L'Hopital's rule does not apply. Does not apply. And if you tried to do L'Hopital's rule, you would get the limit as x goes to pi from the left of the derivative of the top, which is cosine, divided by the derivative of the bottom. Derivative of negative cosine is sine. Okay. And so the derivative of this would be the limit as x goes to pi from the left of, there's a couple ways you could do this. Cosine over sine is cotangent, but you can just say, well, the limit as x goes to pi from the left of cosine, the cosine graph approaches -1 from the left, and the sine graph approaches 0. And by the way, the sine graph would look like this at pi, sine of x, and then the cosine graph look like this at pi. So if cosine is as x approaches pi from the left, cosine's approaching -1. As x approaches pi from the left, sine is approaching 0 from the positive side. So this is approaching 0 from the positive side. So this limit is approaching -infinity, because this is approaching a negative 1, and this is approaching 0 from the positive. Negative over positive is a negative, but if your denominator is going to 0, then the fraction is going to infinity. But this is all garbage because we know the limit is 0. So why do we know the limit is 0? Because if you just literally do direct substitution, you get 0 over 2. So the limit is actually 0. This is actually the correct answer. And if we were to graph it, we would find that the limit equals 0 because you can just plug in pi. Like the function is defined at pi. I can just plug in pi here and get 0 in the numerator, and plug in pi and get 2 in the denominator. 0 divided by 2 is 0. That's a real number. That's not an indeterminate form. So there was a very easy way to do this limit. Just go back to pre-calculus. All you do is plug in pi by direct substitution and you're done. This is this answer down here. This is meaningless. This is garbage. This is totally wrong. So so that's the thing. If you get a limit of a function divided by a function, you must first check that it is an indeterminate form, like we did here. Remember this one. We first said the limit of the numerator is infinity, the limit of the denominator is infinity, and that's an indeterminate form of type infinity over infinity. Because of that, we can apply the L'Hopital's rule. If you try to apply L'Hopital's rule in a place where it doesn't apply, your answer will be wrong, meaningless, and useless. Okay, so there you go. This is enough. All of the problems you're looking at in the homework are of the two types that we looked at in this video. I'm probably going to come back with another video with an example, a graphical example, and then one where the some stuff with trig and some algebra examples. That'll come next. But this is enough to do most, if not all, of the homework that's already up for this section. So, all right, I'll see you next time.